So you would, because I already know it, and then you'd be fine with that, okay? So number 8. Here we have calcium fluoride, and we are given its KSP. We have 30 milliliters of calcium nitrate, so there's the calcium ion. And we have 10 milliliters of sodium fluoride, so there's our fluoride ion. And we have 2 different volumes. When we have 2 different volumes, what kind of calculation do we need to do? We need to do an M1, V1, M2, V2, or a noon. What do you guys prefer? You like M1, V1? I'll do this one as M1, V1. Okay. So here we have M1, V1 for calcium nitrate. And V2 is going to be, what is V2? $40 milliliters. Okay, so for calcium, which is the same as calcium nitrate because it's 1 calcium every 1 calcium nitrate. This is number 8 on the review. Okay. So for calcium, we have M1. Do you like solving it first or plugging in first? Solving first? Okay, so we know M1, we know V1, we know V2. We want to solve for M2, so that's what we don't know. So we have M1 V1 equals M2 V2. And M2 then is equal to M1 V1 over V2. So we plug that in, we get M1 is 8 times 10 to the negative 8 times V1, 30 milliliters, over 40 milliliters. So that is 8 E8 negative times 3 divided by 4 is 6 times 10 to the negative 8. Fluoride, we have, again, we're looking for M2, so it's going to be the same calculation, M1 V1 over V2. But in this case, we have V1 is 10 milliliters, and M1 is the molarity, and V2, of course, is the same because we've combined them both into 40 milliliters. So we get M1, 3 times 10 to the negative 2 times 10 mils over 40 mils is equal to 3e to negative 7.5 times 10 to the negative 3 molar. Now, we want to know if a precipitate forms. So we are calculating the trial ion product. And of course, for calcium fluoride, we have calcium 2 plus and fluoride negative. Oops, we've got 2 of those, don't we? So the KSP, or the Q, or the trial, is equal to the concentration of calcium times concentration of fluoride squared. So calcium's easy, I plug that in. 6 times 10 to the negative 8. Fluoride, do I multiply by 2 before I plug it in? Tell your partner. This came from NaF. So what is the concentration of fluoride? It's just 7.5 times 10 to the negative 3. It's not double that. It just means that when it reacts with calcium, it'll take 2 fluorides to react with every calcium. It doesn't mean that there are 2 fluorides present for every calcium. It just means that's the ratio in which they will react. So we have 7.5 times 10 to the minus 3. And we get 4.5 times 10 to the minus 10. So for our answer, it's either got to be A or D, which if I were a guessing person and I saw 2 of those that were the same and I didn't even know what I was doing, I would probably guess that that's the correct one. Does that make sense? So if you had no idea, yes? Did I not square it? Oh, I didn't square it. Hang on. Oh, I didn't square it. Oh, bad. 6E8 times 7.5 E3 squared. Oh, 3.8 times 10 to the negative 12. So I was wrong? Well. Did you guys get, 3.4. Sorry. There we go. Times 10 to the negative 12. And so it has to be C, regardless of whether a precipitate forms or not. But does it make sense that it should not form? Because this is less than the KSP, which is 4.9 times 10 to the negative 11, which is the case. Okay. Right. That means that it's just barely precipitated and, saturated, just barely saturated, and no precipitate will form. Yeah. I realize that number 11 is for the written response. Oh, but we have it in multiple choice as well, so here we go. Okay, what is true when we mix equal volumes of 0.2 molar calcium chloride and 0.0004 molar sodium sulfate? So this is the same question, but with easier math. Because we are mixing equal volumes, what happens to the concentration? Yes? So when you have these two things, so what we know then is that our calcium ion, once it has been diluted, because we mixed equal volumes, now does anyone want me to explain why when you mix equal volumes you get half the concentration? Yes? Okay. So let's say that our concentration was 2 moles per liter. Yes, of course. Let's say we now double the volume, right? Because we've mixed equal volumes. Yes? Oh, actually, here we go. Let's have our other box with and then we have 4 moles per liter of the red stuff. When we mix them together, we now have 2 moles in 2 liters because the total volume here is 2 liters. I'm not showing it mixing because it's just easier to have it there, but and then we will have 4 moles in 2 liters, which is going to then equal 1 mole per liter, and this one will be 2 moles per liter. Yes? So when you double the concentration, or sorry, double the volume, you half the concentration. Yeah? Okay, so when we have doubled our volume, we're going to half this concentration here, and that's going to be 0.01 molar calcium, because there's 1 calcium in calcium chloride. For our SO4 2-, diluted, that's going to be 0.00020 molar. Our KSP, because they are 1-to-1, will be calcium 2+ times sulfate 2-. If you can't see that ratio right away, you could always write out the formula. CaSO4, Ca2+, SO4 2-. But because this is multiple choice, you don't have to do those things if you don't want to, right? So we now have calcium, which is 0.01, times sulfate, which is 0.0002. 0.01 times 0.0002 is 2 times 10 to the minus 6. So Q, which is 2 times 10 to the minus 6, is smaller than KEQ. And if Q is too small, will it precipitate form or not? No. So it is smaller and a precipitate will not form. Okay, which of the following is the correct relationship between solubility and the solubility product? And remember, solubility product means KSP, okay? And probably the easiest thing to do here is to write your lead chloride, Pb2+ plus 2Cl-. KSP then is equal to Pb2 plus Cl- squared. Now, if we let X be the solubility, yes, we would then have X and 2X. So KSP is then equal to X times 2X squared, which means that KSP is equal to X times 4X squared, which means that KSP is equal to 4X cubed. This is a multiple choice question. If you know that for an AB2 compound that KSP is equal to 4X cubed, you obviously don't need to do all of this work. Yes? If you know that, you can just go straight to KSP is equal to 4x cubed for an AB2 compound. Save yourself a lot of work. Now you would just solve for x. So x cubed then is equal to KSP divided by 4, which means that x, which is the solubility, is equal to the cube root of KSP over 4. Oh, I like number 13. I probably wouldn't give it to you on this test, but you guys have learned enough acid-base stuff that we're going to go through it anyway, okay? So we have silver acetate, AgCH3, COO, solid in equilibrium with Ag plus CH3COO negative. So let's just run through these possibilities. We want to know what would cause more AgCH3COO to dissolve. So if that's the case, which way are we wanting to shift this equilibrium? To the right. Okay, so we want it to go this way. What if we add more silver nitrate? What do we get if we add silver nitrate? Well, we get silver and we get NO3. So what would that do to this equilibrium? Ag plus would go up, so it would shift to the left. Is that what we want? No. Addition of a few drops of concentrated nitric acid, and this is why I say that I would not actually ask this on this test, because what you would need to recognize is that CH3COO minus is a Bronsted Lowry base. So this would be more appropriate on a final exam when you have both units under your belt. Yes? What do Bronsted Lowry bases do? Yes. Yeah, they accept hydrogen ions, which we call protons. Do you guys understand why the H plus ion is called a proton? Yeah? Because basically, if you have hydrogen and you remove an electron, all you have left is a proton. Yes? So it can accept hydrogen ions, and if it does that, you'll have CH3, COO minus plus H plus. What do you get? Yep, or CH3COOH. If we have an organic acid, we will have a tendency to put the hydrogen on the COO group. Okay, but that's not necessarily something that I would expect you to be able to do yet. After the new acid-base notes, we will, but not just yet. Okay, so we have that. What has happened to our concentration of acetate? Acetate is CH3COO minus. What has happened to that concentration? It has gone down. And if it goes down, which way are we going to shift? To the right. which means that silver acetate is more soluble in an acidic solution. Yeah? What would happen if we added sodium acetate? Acetate will go up and we'll shift to the left, which is not what we want. What if we evaporate some water? That would cause less silver acetate to be dissolved, yes, because some of it would come out of solution as the volume of water became smaller. Okay. Number 14. 1 liter. Yes. Oh yeah, for sure. Anytime I move on too quickly, just always let me know. Yeah, no problem. How are you guys feeling about your Bronsted Lowry acids and stuff? Ish? We're going to go over it today once we've done some of these questions. I might not do all of them today. I might do some of them tomorrow. I do want to get some of the Bronsted Lowry stuff done today. So I think we'll do a little bit of a mix and match both days, today and tomorrow. Okay. All right, number 14. 1 liter of a saturated solution of thallium bromide was evaporated to dryness. So we have, you know, an evaporating dish or whatever, and on that we now have some TLBR. And how much do we have? We have 0.56 grams of it. What volume was it in originally? It was in 1 liter, which makes me think I should have used a beaker rather than an evaporating dish, because that's a big evaporating dish if it contained a liter of solution. But doesn't matter. What is the solubility product constant, which is the KSP of thallium bromide? Well, what do we know about thallium bromide? We know we have 0.56 grams in 1 liter, yes? And we know that that is the max concentration, yes? Because that was a saturated solution. And if that is the maximum concentration, that means that that is the solubility. Yeah? So the solubility is 0.56 grams per liter. Now you're right, we cannot work with solubility in grams per liter if we're going to find KSP. We need to convert it to moles per liter. So we're going to do that. And we will use, oh look, weren't they nice to give us the grams per mole, 284. 284 grams per 1 mole. And we get 0.56 divided by 284. And we get 1.97 times 10 to the negative 3. That's our solubility. And if you want to cheat and use, not really cheating, but if you want to use the shortcut for a multiple choice, you know that this is an A-B compound. You know that the ratio is 1 to 1. So what is KSP equal to? Yeah, it's equal to x squared, and x is the solubility, so it's going to be 1.97 times 10 to the negative 3 squared, which is 3.9 times 10 to the minus 6. Hopefully that's one of the answers. Let's take a look. Yes, it is. Woo! Okay. All right, number 16. We have silver sulfate. If it is in equilibrium with a saturated solution, which of the following will result in more Ag2SO4 dissolving? So we want it to go to the right. Yes? If we add SO4, H2SO4, the concentration of SO4 increases and we shift left. We want to shift right. So that's not going to work. Yes? If we add, what if we add more Ag2SO4? Will that cause us to shift to the right? Solids have no effect on the position of the equilibrium. If you think about it, if you have a saturated solution and you add more solid, will more solid dissolve? No, because it's already saturated, right? It's just when you look at it and you're like, oh, this goes up, so it has to shift to the right, you know, and you're not thinking, you know, you're not slowing down and using your common sense, right? How about adding AgNO3? Yeah, Ag goes up and we shift left. What if we add chloride, which precipitates silver chloride? Yeah, our concentration of Ag is going down, so it shifts right, which is exactly what we wanted. Okay. A precipitate of lead chromate is formed by mixing K2CrO4 and lead nitrate. It would be possible to redissolve this precipitate. So which way do we want to shift that equilibrium up here? We want to shift it to the right. We want to redissolve the precipitate. We could add a concentrated solution of, will increasing chromate work? No, because that would shift it to the left. Would increasing dichromate work? Well, no. It would cause this to increase, which would cause this to shift to the left, which would cause an increase in chromate, which we just said does not help us. So, no. A strong acid. What would an acid do? A strong acid contains what? Hydrogen ions, yes? Oh, look, what do we have here? Oh, we have hydrogen ions. So that will increase the concentration of hydrogens, which will cause the bottom equilibrium to shift to the right, which causes chromate, CrO4 2- to decrease, yes, which will cause this to decrease, which will cause that to shift to the right. So it's like a chain reaction. Yeah? You look puzzled. Yeah. So we increase this. This shifts to the right, which uses up chromate. So chromate decreases. And when chromate decreases, the top equilibrium then shifts to the right and this redissolves. Okay. Yes. 21, yes. A beaker contains an unsaturated solution and some solid solute. So we have in our beaker unsaturated and we have some solid solute. Is it true that the rate of dissolving of the solid is 0? Is there no dissolving at all? No. There's always dissolving. Okay, if there is solid present, there will always be dissolving taking place. Is the rate of dissolving equal to the rate of precipitation? Is it true that for every one of these reactions where it dissolves, another particle will precipitate? If that was the case, what kind of a system would we have? The system would be at equilibrium if the rate of dissolving equals the rate of precipitation. And if we are at equilibrium, what kind of a solution would we have? That would be a saturated solution. Oh, we are unsaturated. So it's not that either. Okay? So now we have to decide if it is unsaturated, is it dissolving faster than it is precipitating? Or is it dissolving slower than it is precipitating? It's dissolving faster because eventually it's going to become saturated. The only way to do that is if you're dissolving faster than you are precipitating. So in an unsaturated solution, it's always going to be the case that you have dissolving faster than precipitating. And then once the two are equal, then you are at equilibrium and you have a saturated solution instead. Number 22. We have 1 mole of copper, or 1 times 10 to the minus 3 moles of copper, and 9 times 10 to the minus 3 moles of OH minus added to 1 liter of H2O. Which one of the following is the correct value for the trial KSP, CuOH2? Well, the KSP, because it is a 2 to 1, we will have copper and we will have hydroxide will have to be squared, yes? Because of that 2 there. And so that's going to be equal, oh, it's a 1 liter solution, so my moles is the same as my molarity. So that's going to be 1 times 10 to the negative 3 molar times 9 times 10 to the negative 3 squared, which is, no? How much OH did I put in the beaker? I put 9 times 10 to the minus 3 moles in it. There's no way I can magically get 1.8 times 10 to the negative 2 moles. Yes? Because we're putting them in separately from one another. Yeah? So that would be 1 times 10 to the negative 3 times 9 times 10 to the negative 3 squared, which is 8.1 times 10 to the negative 8. Number 25. consider the following equilibrium, which will increase the solubility of Ag2CrO4. Well, we can't add CrO4 because that'll shift it to the left. We can't add silver because that will shift it to the left. Adding more of the solid makes no change. But Ag and I will precipitate one another because they are low solubility. And so that's going to cause the concentration of silver to decrease, and that's going to cause, let's see, silver decreases, and therefore it shifts right. Okay. Oops. Yeah. Number 28. What will happen when equal volumes of potassium carbonate and sodium phosphate are mixed? Both of your cations are alkalis. And what do you know about alkali ions? They're soluble with everything. So, are we going to get any precipitate? No. Which of the following solutes could dissolve produced at least 0.1 molar? What do you know about 0.1 molar? Why should that number ring a bell? That is the minimum required to be considered soluble, okay? So where would you look? Solubility table, or you could say, I just answered a question that I know the alkali ions are soluble with everything. And I know that I'm only allowed to choose one answer, therefore my answer must be Na2SO4. You can, of course, confirm it by saying, what about iron and zinc, aluminum with sulfite? We can go there and we can say sulfite, iron, and aluminum. And I forget what the other one is, but it's definitely only the alkali ions, ammonium and hydrogen, are soluble with sulfite. So. And I think that's as far as I got with circling things, and that seems to be about half the questions. So I'm going to leave it there for today, yes? 22, yes. Yeah. I'm recording this, by the way. So, yeah, so that'll be helpful, yes? I think I'm recording it. Let's check. Am I? Yes, I am. Yay! Okay, otherwise you'd be like, yeah, she's recording, and I'm like, oops, I did not, but I did. Yay. Okay. So I think at this point it would be nice for us to do a little acid-base stuff, okay? Get a little fresh perspective. I know that going through those questions makes me a little tired. I don't know about you, but yeah. So we are going to look at 4.1F that you just got today, okay? And the purple sheet that I gave you is exactly what is in your data booklet, except that I thought it would be nice if you had one you could write all over. Yes? So this can be the copy that you can write all over, but it's still purple, so it's easily findable. Yes, of course. If you did not pick up those handouts yet, you will want to do so. Hi?
So the answer for 25 is A, right?
25 is A, yes.
Because when we add AG,
when you add I, it will
solid,
precipitate with the AG, and the AG concentration will decrease.
Because solid, it doesn't make any.
That, I mean, they're all solids, but this is the solid that is here. Yeah. So yeah, exactly. Yeah. Thank you. So if a chemical is acting as an acid, what does it do with its proton? This is 4.1F, the stuff you just got today. Did we not watch the videos? We did. So what does an acid do? A Bronsted Lowry acid, by definition, sorry? Yeah, it donates a hydrogen ion, okay? It donates a proton. So it is going to, an acid loses a proton, and don't forget that a proton, of course, is H plus. And if the only other substance around is water, then it will lose that proton to water. What will water become? If I had an acid, HA, and it reacted with water, H2O, and a hydrogen ion, this hydrogen ion is transferred to the water, what does water become? Yes? It becomes the hydronium ion, yes? So we are left with A minus plus H3O plus, and H3O plus is known as the hydronium ion. So although up till this point we've been showing acids as simply dissociating in water, in reality they don't just dissociate in water, they react with water and give it a proton. Yes, so it's actually a little more complicated. So I like to say that this is reality, right? This is reality. And if we were to write it just like this, HA becoming H plus A minus, that's like, and I know you guys don't know what shorthand is, but have you heard the word shorthand? Okay, there used to be, when it was important for people to have secretaries, right, so that they could like say something and have someone take it down very quickly. Shorthand was a series of symbols that allowed people to write things very quickly. It was almost like a different language. It's just, you know, there were certain symbols that represented words, certain symbols that represented syllables, so that you could write very, very quickly. And so shorthand just means writing something in a short form that's not exactly the same. Yes? So this is our shorthand version, but this is reality, okay? And we will use both, okay? Because sometimes it's just convenient to use the shorthand method. So when a substance loses its proton, when an acid loses its proton, it turns into a chemical species called the conjugate base. Are you familiar with that term? Was that a term that you heard? Yes? Good. So if we were to write the conjugate base for HCl, so to go from, thank you. Thank you. So to go from a Bronsted Lowry acid to a conjugate base, what has to happen is that a hydrogen ion has to come off. So what would we end up with for the conjugate base of HCl? Cl minus. Pretty straightforward, yes? And you have to remember that it's not just H that comes off, it's H with a positive charge. So HCl is neutral. If it loses H plus, it loses a positive charge, it becomes negative, yes? What about HSO4 negative? What is its conjugate base? SO4, and then yes, we have to take that negative. Now we're losing a positive charge, so it's going to become 2 negative, okay? And HPO4 2 minus would become PO4. We take off the hydrogen, and it becomes 1 more negative than it was before. So it was 2 minus, it becomes 3 minus, okay? So remove a hydrogen and make it 1 more negative than before. Now, if you have a substance acting as a base, instead of donating a proton, what does it do? It gains a proton or accepts a proton, okay? And it will turn into its conjugate acid. So when we go from having a Bronsted base turning into its conjugate acid, we're going to have coming in here a hydrogen. So we're going to add an H and we're going to add a positive charge. So what is the conjugate acid of CO3 2 minus? Yeah, so we have H, we add an H, and then it's CO3, and it used to be 2 minus, but we added a positive charge, so now it's just negative 1. How about CH3COO minus? This is CH3COOH. And remember I said this more earlier that I wasn't expecting you to know that the hydrogen goes on the end? Well, now I am, okay? In an organic acid, which is, do you guys remember what organic compounds are? Carbon-based, yes. The detachable proton, okay, which is this one here, that's the only proton that is detachable, and it goes on what we call the carboxylate group, which is, you know, not that important for chemistry 12, but if you're taking biology 12, it will be, and if you're taking university chemistry, it'll be important. Okay, so that carboxylate group is the COO negative group. And once the hydrogen attaches, it forms COOH, which is known as the carboxylic acid group. Okay? However, like I said, most of that is unimportant unless you're taking bio or unless you're going on to chemistry in university, in which case you should be aware of that. Most of them are more straightforward though. What if we have HPO4 2 minus? Tell your partner, who is its conjugate acid? Yeah, we have to have 2 H's instead of 1 H. PO4, and it gains a positive charge, so instead of 2 minus, it's just minus 1. And if we have HCO3 minus, what does that become? H2CO3, and now it is neutral because it gained a positive charge. It was -1, we added a positive, it becomes neutral. We're going to back off a little bit here so you can see the whole thing. It might be easier for you to look on your own sheet since this font will be fairly small if we're looking at all of them. Do you notice anything in these lists that is acting both as an acid and as a base? HPO4, yes. We got HPO4 here, and we have HPO4 2 minus here. Okay, so HPO4 2 minus. And who's the other one that we see? HCO3 minus. Do you see how it's here as an acid and it's here as a base? So HCO3 minus and HPO4 2 minus can either donate or accept a proton. Chemicals that can act as either an acid or base, what are they called? See if you can remember and tell your partner what you can remember. Amphi something. And what are they giving or taking? A proton, therefore they are amphiprotic. Yes. Okay. Sorry, yes? Oh, I thought I heard my name. No, I'm just going crazy. That's okay. Did my picture of the frog help? I actually spent a fair bit of time trying to find that perfect picture of the frog. This was years ago now, but yeah. Another definition of amphiprotic is a substance that can act both as a what donor and a what acceptor. Proton. You could say H plus. And in fact, we'll put both of them there for now so that you get used to seeing them interchangeably, yes? Amphi is from the Greek, meaning on both sides. And once again, we mentioned that amphibians can live both on land and water. And I think it's the same root as ambidextrous, which means you can use both hands, right? So if you're going to recognize amphiprotic substances, if you are going to donate a hydrogen, you must have a hydrogen. So if a substance doesn't have a hydrogen, it is not amphiprotic. Does that make sense? If you're amphiprotic, you need to be able to donate, so you must have a hydrogen. Now, most of the time, an amphiprotic substance is going to have a negative charge, because if it is negative, it will be attractive to the positive proton. Yes? So it's going to have a negative charge. In other words, it will be an anion. There is an exception to this second one, and the exception is water, which is always amphiprotic, even though it lacks a negative charge. All the rest of the amphiprotic substances will be negative, okay? In order for an acid to act as an acid, there has to be something else present to act as a base. You cannot have an acid if nobody is there to accept the proton. Okay? And all acids have some degree of losing their protons, and this is their relative strength. How are you guys feeling about that table after having watched those videos? Good-ish, a little confused? Okay, so we're gonna go through it again. And if you want to have a color printout of this, it's like literally color coded. So your acids are all red, because what's one thing that acids do? What's one of the characteristics of acids? They turn litmus paper red. So I've put all the acids in red. That's okay because acid is red, okay? Bases, what color do they turn litmus? They turn it blue. And so you can see on here, all your acids are red and all your bases are blue. There's even color gradation, yes, where you can see that the strong acids are in darker red and the weak acids are in lighter red. The strong bases are in dark blue and the weaker bases are in lighter blue. There was a question, yes. Litmus paper is an indicator, yes? So we'll actually be looking at a lot of acid-base indicators. Yeah, acid-base indicators appear one color in acid and a different color in base. Yes? What's it made of? I don't know. Like, it's gonna be some organic compound like C blah blah de blah. I don't know. Some complicated formula, probably involving a ring structure with a conjugated double bond, which means alternating single double, single double, single double. Okay. Do you want to know any more? No, didn't think so. Okay, good, good, good. Now, you'll notice on here that although we have strong acids, weak acids, strong bases, weak bases, we also have some areas in yellow. What are those? They're on that side, but they are too weak to actually be bases. You'll notice that the arrows do not go in the reverse direction. You guys can continue working on your review for tomorrow if you haven't finished it yet. If you want a little preview, you can read through this, but we'll finish this up tomorrow as well. Hi.